stains my arms. I think I finally understand it now. Oh, life's much too long to not fall in love, but much too short to keep waiting around. We run ourselves into the ground. Oh, I'm terrified to tell you. Ooh, but deep down I think you already know. If patience is a virtue, ooh, then you're the greatest person I've ever known. Ooh. Why can't I get it through that head of yours? I'm only gonna leave you broken. You'll remember me with tears in your eyes.
Hi Orbeez! We're gonna actually start on time today, or I guess 3 minutes past. Okay, actually I'm kind of late, but it's okay. We're gonna get started. Oh, the music ended abruptly. Speeding at Seas, Macy. Hello everybody. I hope everyone can hear me all right. I had to adjust the audio settings from the collab last time, so I hope all is good. Whoa, why isn't my mouth moving? That's so weird. Let me fix that real quick. Of course, it would not be a Z stream without some level of technical difficulty, so... Alright, I think that's fixed. Okay, yes, okay, we're back. Hello everybody, I hope you are all doing well. I just saw that Eggy has an essay due in 30 minutes, so we're gonna quickly zoom through attendance. Hello Matt, hello Arky, hello Zilla, hello Sirna, hello Caffeephile. I'm also a Caffeephile, I guess, in a way, if you've noticed my little cup here. Hello Matt, I think I've changed the Twitch stream name now. I don't know, every time I start it up, it always reverts to what my previous stream was, but I think it's fixed now. Hello Liam, let me know what your question is. Hello Parafergon, hello Warpy, thank you for stopping by, even if it's briefly. Hello Eggy, I hope you're locking in. Oh, hello Aleph, thank you so much for stopping by, good seeing you. Aleph is doing math VTubing content very soon. Super exciting stuff. Yes, good luck Eggy, and may that essay go well. That is for sure. I am a tea enjoyer. Actually, I did have some delicious London fog today. I feel like there's this cafe I usually go to, and I've never gotten their London fog, and I got it this time, and I was actually blown away. It was great. And on the Twitch side, hello Childrew, hello Lena, and hello Vranius. Very cute emojis. Woohoo! Yes, hands. I brought back the hands. I usually disable hand tracking for collabs, but yes. This coffee cup is a little misleading because I actually don't think I had coffee today. Oh, I did have more caffeine than usual today. No, I did have a decaf coffee in the morning. I made myself like a decaf cappuccino just with like the powder, and I like whisk it up. And then I had some chai tea with milk. Then I had that London fog. Yeah, I think I had those 3. So 3 caffeinated beverages, I guess. Currently drinking some orange and spice tea. Delicious. I hope you're enjoying. Yeah, let me know what your favorite type of tea is. Thank you for joining me for this rare evening stream. I've actually noticed, I think the last time I did like an evening stream has been like, it's been a while. But I'm glad that I am now here, and hopefully I will be able to see some new Orbeez faces who have typically been unable to, you know, join these streams in the past. So yeah, yippee! I also decided to do a weekday stream because, oh my god, I've been trying to plan out this weekend streaming schedule, but it has been so challenging. So I was originally planning to collab with Nep, but I actually got some plans in the way. So I might not be able to join for that, but we are planning on another collab, so don't worry about that. And then I thought about doing my 7K celebration which the members already know this, but I guess I'll sort of announce it to the rest of you guys. I'm planning to do Kerbal Space Program again, and releasing a surprise video. And I was thinking about doing that this weekend, but of course, I think I'm gonna just be like fully out of town, so that kind of threw all my plans out the window. Evening stream is 4:30 a.m. Oh my god, well thank you Humpy for joining. Please get some sleep for sure. Chai tea. Chai tea is delicious. I actually didn't really like chai tea in the past, but I realize now that mixing it with milk is really good. I also think that at least the chai tea that I had was like, this one was black tea, but some other chai tea I've had in the past isn't caffeinated. So I feel like it's a good like afternoon pick-me-up. Yeah, chai tea with some cinnamon. And I also heard that chai tea has like antioxidants or whatever. So that's also great too. Yeah. For the American Orbeez, you guys may know that this is actually, this upcoming weekend is a long weekend because of President's Day on Monday, which is why things have been, like, more in the air than ever before, because it's just, like, a nice, like, 3-day weekend. I'm curious if you Orbeez have any fun plans for the weekend. Do let me know, I'm very curious. Ah, yes, Chinese New, yeah, Lunar New Year, yeah, no, I do know that my friend's going to some sort of like a festival for that where they're doing like a little market, which is going to be very exciting. Yeah, that's going to be great. In terms of other really great news, this is coming up. So, well, actually it's already out. So if you have not seen already, I reposted this on my X account and also made a post on Reddit because apparently I am the Reddit whisperer amongst VTheorem. But as some of you guys, maybe as most of you guys may know, I'm a part of this amazing group called VTheorem. We're a group of IRL scientists, passionate about science communication, and we have been distributing this form. If you are interested in hearing more about our next generation, there's going to be auditions for it soon. So this is just an interest form. It is not signing up for our auditions is not an audition. Etc. It is just demonstrating interest so that you can make sure that you're in the loop and getting the emails and posts when we send them out. VTheorem has been my home, has been an amazing space of really talented, creative content creators, and I really, really encourage you to fill out the interest form. Or at least if you're not a VTuber or still passionate about science communication, be sure to follow us on X and so forth. Yeah. Please go with them. There's going to be some good tea. Oh, yes, no. But the thing is, this is a friend that is not, like, in my area. Let me just quickly do the VTheorem little ping here. Where do we send the Valentine's chocolate? Oh, yeah, no, I love chocolate, but, I mean, I do have a throne if you want to send me stuff there. I have been having some issues receiving some of the gifts recently, which is why I haven't done a full unboxing stream. But I think it should be resolved now. The throne, help support team has been, like, they are so on top of it. So they've been really great. So I'm gonna put this VTheorem announcement into the corner. Yeah, I wonder, are you guys doing anything for Lunar New Year as well? One thing that I'm planning to do is that my friend is in an improv group, and they are performing on, like, the improv group as a whole is performing, and it's, like, Valentine's Day themed. I think it's, like, themed after, like, I don't know if you guys have watched, like, Love Actually, where it's, like, sort of, like, short stories. They're kind of going for the same premise where they have like various like short stories. I don't know how this is going to work through improv. I actually think that improv is really impressive. Just like hearing like very little preparation. I'm visiting grandma. Oh my god, have fun, Eggy. Have fun, have fun. Yeah, no, so that's going to be a great time. And this past weekend, there was the Super Bowl, so I got to enjoy a really nice watch party for that. So, yeah, no, things have been good. Albeit also very busy. I have no plans Well, another thing about this weekend is it's not just the long weekend, but it's also Valentine's Day weekend, which will be a lot of fun. I also know that historically Faye and I have collabed on Valentine's, but as I mentioned before, we are meeting IRL very shortly, so that will be very exciting. I don't think we're gonna stream anything for that, but that will, you know, pay tribute to our yearly tradition of somehow collabing / meeting regularly on Valentine's, which will be super cute. We'll at least enjoy a nice box of chocolates, or get some flowers. I also think that since Valentine's Day is on a Saturday this year, it will definitely be a lot more crowded and crazy than it has been in previous years. Though, yeah, no, I think it's been... I don't know, I do really like the vibes, like, leading up to Valentine's. You know, I feel like there's, like, bouquet making stuff, you know, a bunch of stores are doing, like, giveaways. I just submitted, oh my god, thank you. Love Actually, aka film set in a reality where TSA does not exist. Actually, that's so true. Wait, my criticism of Love Actually is that I feel like a lot of the stories are kind of weird. Like, I don't want to spoil it, but like, there's, okay, spoilers for like 10 seconds, so mute if you haven't watched it. There's one where like the dude like cheats on the wife, and I just like didn't like that one. Okay, spoilers over. It was like specifically that story that I just didn't like. So yeah, but we'll see how the improv show goes. Maybe they'll make it more wholesome. Yeah. Alright, let me get my little article set up. So today we're going to be going through wrong one. This one. We're going to be going through 3 Astrobites articles. I just pinned the first one. And I think I'm going to aim for about like an hour 30-ish of a stream, or maybe a little less than an hour 30. So, yippee! What does love even feel like? It's okay, Joseph. Pat. I will pat you on the back. Never cheat on Z, she'll get revenge. What? I'm not cruel. Wait, do you think I would enact revenge? Sorry I'm late stopping by to say hi. Thank you so much, Stella. Actually, thank you so much for stopping by. Great to see you. Alright, cool. I think without much further ado, we should get started on the first article. Wait, let me get my short blurb on Astrobites first. Stay hydrated, Orbeez. My voice is certainly a lot better than it was a few weeks ago, which is great. What was I gonna say? Yes, Astrobites. So I'm sure all of you guys have already heard the spiel already, but for those of you who are new, Astrobites is a website that takes existing scientific research articles and translates them into a more accessible format. In this case, we are taking a look at research that's being done on clumpy galaxies, which is an interesting feature of some of the first galaxies that we see in the universe. So feel free to ask questions. In the past, we've done some like Astrobite streams on topics that are less so my area of specialty, but I do really like galaxies, so feel free to ask away, and I'll try my best to answer them. But of course, this is a learning environment, and I'm not like a textbook, so we'll also Google some stuff together if we have to. So yeah, this is gonna be great. And of course, feel free to just chime into chat. I'm hoping to go for like a pretty chill vibe because my past few streams have been collabs, and I've also just wanted to catch up with you all and everything. So, all right. With that out of the way, without much further ado, let us get started. So the first article that we have here is by Nilufar Sherray, titled "When Galaxies Get Clumpy, JWST maps the birth and death of star-forming clumps." And at the top of each of these articles is the actual research paper itself. So we'll be taking a look at this article. All right, so let's read. If you look far back enough in time, maybe I can make this a little smaller. Oh, whoa, whoa, whoa. Okay, we're gonna keep it that size. Okay. Clumpy clumps. Yes, so I wonder if they have a photo. Yeah, literally like clumps. See these little clumps here? I feel like there's better photos of clumpy galaxies, but that's one example of a clumpy galaxy. All right, so let's start. If you look far back enough in time, galaxies often look lumpy rather than smooth. Instead of familiar spirals or ellipses, you see many bright knots across these galaxies. These knots are star-forming clumps, compact regions a few thousand light-years wide, lit by fresh stellar populations. Clumpy galaxies are common. In Hubble images of the early universe, astronomers could see that many galaxies around redshift 2, a time known as cosmic noon when star formation reached its peak, were dotted with kiloparsec-scale knots of light. Some of these clumps hold as much as 1 billion solar masses in stars. Two main ideas have been put forth explaining the origins of these clumps. One suggests that clumps form within the galaxy itself when its gas-rich disk becomes unstable and fragments, a process called violent disk instability. That is such a cool name. The other argues that at least some clumps are small satellite galaxies, so like little guys, that have been pulled in and disrupted. Both likely play a role, and the challenge has been figuring out how much each contributes. So what does clumps mean in this context? So appearance-wise, we see clumps visually as literally these like little lumps in the galaxy. And they are regions, as you may notice here, they're blue, which is actually indicative of the fact that they experience more star formation. So more young stars are being born. And the reason why that looks blue is because younger stars are bright and blue, and they don't live for a long time. So when a region is undergoing active star formation, it has these bright blue regions because it's with these newborn stars. Versus an older region of the galaxy doesn't have these blue stars because those blue stars die out very quickly. And so this blue light, these blue clumps, are indicative of this fact that they are regions where we are seeing more stars being born. And there are also regions where sort of the gas looks a little bit more lumpier. Those are unimaginably large clumps. Yeah, no, there's some crazy ones. Actually, wait, hold up. There was like, I mean, there are some galaxies with like a lot of clumps. Yeah, there's one with 15 clumps. Yeah, let me see if I can pull it out. Yes, I think this should be okay to share because it's a space.com article. Oh my god, that scared me. Thank you, Neltarina, for following. So this is one of the examples of the clumpiest galaxies that I just thought of off the top of my head. It has 15 clumps. There was a paper in Nature that explained this, but literally you see that it is the clumpiest boy imaginable. This is also known as cosmic grapes for that reason, because it looks literally really clumpy. Hello Z, late stream, I like it. Thank you, Santos. Thank you for joining. So like spinning pizza dough falling into pieces. Well, one of the ideas as to how these clumps form is that there's little galaxies that sort of come into the bigger galaxy and they kind of revolve around and around, but they don't quite get like fully mixed. So if you think about like, what's a good example? Like, let's say that you're like baking, right? And you're trying to like stir the lumps out. Over time, if you like stir it enough, the thing that you're baking, like the liquid kind of like evens out. But before that, the lumps kind of like move around with like how you're stirring, right? One of the theories as to what the clumps are doing is something similar to that. Cosmic grapes, I like that name. Yeah, no, it literally does look like grapes. This is a very extreme example. Typically we see, I think like roughly like 2 to 3 major clumps. And I think in the example shown here, they have about like, I guess they have 6 clumps, I think here, but let's take a read. Love me some cosmic background radiation. Thank you so much. I'm canonically a photon from the first light of the universe. But one explanation was that the gases in the disk start separating. Well, it's more like the gas that is brought in from these satellite or these smaller galaxies starts to become more, oh my god, it's not, the word isn't accumulated, but accreted. It becomes to accrete into the disk, and then leads to its more smoother appearance. A home-style galaxy, yes. Delicious. All right, so let's read on. Using data from Canadian Near ISS Unbiased Cluster Survey, or CNUCS, the team measured the masses and ages of more than 20,000 clumps in nearly 4,500 galaxies, spanning redshift 0.5 Z to, Z is 0.5 to 5. So Z is sort of like a measure of time. That's me. That's me. This large sample lets the team follow how clumps form, grow, and eventually fade as their host galaxies evolve. CNUCS targets 5 massive lensing clusters and their surrounding flanking fields with both the NIRCam and Near ISS instruments, combining James Webb Space Telescope's resolution with the legacy of Hubble imaging. The resulting data are able to reveal clumps that are smaller than a kiloparsec, even in galaxies billions of light years away. That is really impressive. That is really impressive. I think the size of the first galaxies was about a few hundred parsecs, and then later on they span like a few kiloparsecs and later tens of kiloparsecs. So being able to resolve it at such a crazy distance is definitely impressive. I think the Milky Way is, wait, I'm just doing quick. I was gonna say 15, yeah. So the Milky Way currently has a diameter of 30 kiloparsecs. That's actually probably a better measurement because they're looking at galaxies that are sort of nearby, ish. That's what the 0.5 to 5 redshift range was suggesting. So we're really going like in depth into these clumps. So so what was that violent thing explanation? So the idea was, oh yes, so the idea is like the disk of the galaxy could fragment and form these clumps temporarily. And if you go here, I believe they also have a, wait, let me check. Let me see what that leads to. Oh, interesting. It leads to another Astrobites article, but not on galaxies. Wait, interesting. Wait, I'm gonna see if I can play this first. Okay, this is interesting. I'm gonna show this real quick, actually. So if you click that link, it leads to this article, and down here there's a video that shows how fragments can form in disks. So you see like the spiral arms are rotating, and then because I think the arms are sort of colliding with another, you're getting these little clumps naturally. That's interesting. I actually didn't know that they would form like that. Whoa, my face is frowning. It's because I was like, I had my hand on my face, and so I think the tracking broke. Yeah, no, that's really interesting. Yeah, no, for the violent disk instability method, they are suggesting that it is not due to mergers. It's just the galaxy's natural rotation leads to that. Yes, competition astrophysics love this. Yes, I love it. I love these visuals. That's great. That's actually really cool. Yeah, so they have these two methods. Finding the clumps. To identify the clumps, the authors mapped stellar mass and ultraviolet light across each galaxy using JWST images. They then searched for the compact UV peaks that stood out from the surrounding disk. To ensure these detections were real and not noise, they injected fake clumps into the data and confirmed that their method correctly recovered most clumps above 10 to the 8 solar masses. And so they have an example here. So they have one example here. So Z equals 3. So that's around the cosmic noon. So afterwards, galaxies started to sort of stabilize. And so they have the clumps here. They look at the galaxy in 3 different filters, which they map to blue, green, and red. And then they have this, what is this? This is just a map of the mass of the galaxy. And then they have the rest from UV maps. So that's important because bright star-forming regions are bright in ultraviolet. And then they have these detections that they've circled here. What's really interesting is that there's been a big question about whether or not these clumps are also massive. As in, are these clumps just temporary periods of star formation, or are they actually like garnering mass. And it seems like from this side-by-side map that these clumps aren't appearing in the stellar mass map. I wonder if that's one of the conclusions that they found in here. All right, let's see. How common are clumpy galaxies? If you look at figure 2, okay, we'll scroll down later, which shows how the clumpy fraction changes over cosmic time, one trend stands out clearly. In the early universe, around redshift 4, roughly 40% of the massive galaxies contained at least one bright clump. That fraction rises to nearly 60% by redshift 2. Wow, when star formation activity across the universe was at its peak. After that, towards lower redshift, or more recent times, galaxies become more settled and the clumpy fraction declines again. And I think that actually might be attributed to the fact that galaxies were merging and interacting with each other much more in the early universe. There were a lot of merging events, especially as the galaxies formed and grew over time. Smaller galaxies tell a quieter story. Systems with masses between 10 to the 8.5 to 10 to the 10 solar masses sit near a 30% clumpy fraction. Okay, interesting. Across the entire time period, so they actually don't change in clumpy fraction. Okay, the authors note that this value might be slightly underestimated since clumps in low galaxies are harder to detect, and some are likely missed even after applying corrections. In other words, the biggest galaxies were the messiest at cosmic noon, while the smaller ones maintain a steady but milder level of irregularity. So merging seems to be more likely than VDI. I'm not really sure what they're implying here, but I would assume so because the fact that these smaller galaxies are still very clumpy, I think is indicative of the fact that it must be due to merging. Because if you have a galaxy that is like 10 to the 8.5 solar masses, I guess they don't really have a visual here, but you're also sort of approaching like the smaller galaxy range where these galaxies don't have well-defined disks yet. And it seemed like from the animation that we just saw that those clumps that occur from the VDI method, the violent disk instability method, would arise from the galactic arms rotating, but that doesn't happen when there's no disk. Another factor of these galaxies that I'm thinking might also be a factor is that in smaller galaxies, when a star dies, it explodes and it goes supernova, right? For a larger galaxy with a disk, that the energy released in the supernova actually sort of vents perpendicularly. So if you think about like the plane of the Milky Way, and you think about like kind of going up and down from it, that's sort of where the explosions happen. It doesn't go out like to the side. And as a result, the disk is preserved. Versus smaller galaxies, what happens is that when a supernova event takes place, the entire galaxy basically just like explodes, and that material has to come back in again. And that instability, I'm wondering, might also lead to some of these clumps because they're basically having to re-merge again and again. Yeah, I think they kind of suggested here. The biggest galaxies were the messiest cosmic noon, while the smaller ones maintain a steady but milder level of irregularity. This supports the idea that gas-rich disks are prone to fragmentation. So the disks themselves probably are more prone to the violent disk instability method that they're suggesting here. Yeah. Oh, this is a great plot. Yeah, so they're showing here the blue ones are the lower mass galaxies, and the red ones are the massive galaxies, and they're showing that. I wonder where these gray symbols are. So earlier studies. So it kind of peaks at redshift 2. But for the lower mass galaxies, the fraction of clumpiness is less and it remains roughly the same. Whereas there's sort of a slight increase as we go from, so redshift 0 is present day. So this is like the earliest universe, and then this is today. And so the fraction of clumpy galaxies for the more massive ones go up and then down a little bit. I actually have some opinions about having plots with redshift this way or that way. Technically, it does make sense for the redshift to go from like increasing order because, I mean, like that's how we perceive numbers. But if you think about cosmic time, the progression of time is actually from this way to this way. It's such a small little tidbit. Some people have different opinions about this. All right, so the team, oh yes, okay, this is exactly what I was curious about. The team also measured the clump stellar mass fraction, which counts how many clumps exist at each mass. In nearby galaxies, the masses of star clusters and molecular clouds tend to follow a power law with a slope around -2, meaning that small clumps are common while massive ones are rare. Across the full sample, the same pattern appears. The CSMF slope stays close to 2 from redshift 5, let me zoom in a little, to the nearby universe. That consistency hints that the basic physics of clump formation hasn't changed much over the past 10 billion years. That is interesting. The basic physics... I'm wondering how they extrapolated that. Just because the slope of the clump mass remains the same, I'm not really sure how that would imply that the physics of clump formation would stay the same. Because there are some physical processes that are more prominent at the early universe, or as a result of more, I guess, the physics, maybe what they're suggesting is that like the physics of the universe really hasn't changed much, which is true, but I must leave stream for now. Hopefully get me back before it ends. Thank you so much, CapFile, for joining. Interesting. But when the authors separated the clump sample by host galaxy mass, the picture becomes much more interesting. In more massive galaxies, the mass functions have flatter slopes, meaning that these galaxies host proportionally more heavier clumps. In smaller galaxies, the CSMFs have steeper slopes, indicating populations dominated by lighter clumps. This connection points towards the idea that a galaxy's own environment, its gas content, disk size, and internal motion, helps set the balance between large and small clumps. Yeah, that makes sense. So I guess what they're showing here is that they have the lower mass galaxies here on the left, and so there is a steeper slope versus these higher mass galaxies, which is a little bit more flatter. And that suggests that a galaxy's internal conditions for higher mass versus lower mass galaxies influence how its clumps form and survive. You are a star. Oh, thank you so much, Ocean Man. Does light get slower over millions of years? Nope, the speed of light remains the same. Does gravity become weaker? No. The physics themselves are the same, but I think what this... I obviously should go to the original paper to see what exactly they're saying, but I think what the Astrobite is suggesting is that the physical processes that govern the formation of clumps, whether it's from the violent disk instability like we saw earlier with the clumps kind of forming naturally due to the rotation of the galaxy, or because of smaller galaxies coming into the bigger one, that physics stays the same. I think that's sort of what they're getting at. Does time go faster? Well, no, but the scaling of redshift as a unit is definitely very interesting. So redshift is a way that that astrophysicists sort of measure time. As I showed before, redshift 0 is present day. And although these redshift numbers are spaced evenly, they are actually in time very different. So if it has to do with like the expansion rate of the universe and so forth, but the time between redshift 1 to redshift 0 is a lot longer than it is between the time between redshift 5 and redshift 6. But time itself doesn't move faster. This is just a consequence of how we've defined redshift as a unit. I hope that answers your question. So what controls the shape of the clump population? So why would more massive galaxies host larger, more heavier clumps? One explanation is gas content. In theory, gas-rich disks are more unstable and can collapse into larger fragments. When the team estimated gas fractions using scaling relations, they found a mild trend. Galaxies with higher gas content tend to show shallower stellar mass function slopes, meaning more relative clumps relative to smaller ones. However, when considering only the youngest clumps, the slopes shift closer to -2. This likely reflects a larger population of recently formed low-mass clumps that have not been disturbed or merged. Over time, dynamical effects or clump mergers may preferentially remove or grow low-mass clumps. So I guess I'm wondering, is it equally likely, are these dynamical effects, so I guess the rotation of the galaxy or the merging of different clumps, would that lead to remove or grow? Like, I did read a research paper about how these clumps are actually only very temporary phases of which stars and gas reside. So I'm curious to see, you know, is it more likely to remove the clumps or grow them? Another factor may be ex situ clumps, formed in smaller satellite galaxies that later merge with the host. These accreted clumps tend to be more massive, yeah, because they're literally smaller galaxies, which can also flatten the mass function. In reality, both processes are likely shaping the clump population. So let's see. So the estimated gas fraction, each point represents a redshift bit. So, okay, so we have the color being redshift. Oh, and this is the slope. So Young's clumps tend to have steeper slopes. So the young clumps are the circles. Okay, yeah, so they're down here. While the full population is slightly flatter due to clump disruption or growth over time. So this work specifically focused on the young short-lived clumps. The fate of the clumps. Survival or destruction. Not all clumps live long. Stellar winds, radiation, and supernovae can blow away the gas that holds a clump together, dispersing it into the galaxy's disk. To test how this affects the population, the authors compared young clumps to older ones in massive galaxies. As shown in figure 5, the mass function of the younger group is steeper, meaning that many low mass clumps are present. The older population lacks these lighter clumps and has a flatter slope. This difference cannot be explained by simple stellar aging. It suggests that the low mass clumps are gradually destroyed while the massive ones endure. Some of this may also reflect cosmic evolution. So what happens to these more massive clumps? Interesting. Taken together, these results point towards a picture of clump evolution. Galaxies constantly form many small, short-lived clumps, but only the most massive ones survive long enough to grow or migrate inward. Those survivors withstand both feedback and dynamical shear, which is the galaxy's rotation tugging on clumps at different speeds and stretching them apart and then tearing them apart. Over time, these long-lived clumps can spiral towards the galactic center and contribute to the growth of bulges. Okay, this is really interesting because... Is it like Agario again? Yeah, but this time with clumps. Gravity holds the more massive clumps together. Yes. This is interesting because there has been a lot of debate about what are the roles of these clumps, because we've been seeing a lot of clumpy galaxies in the early universe, but the real question is whether they contribute to the growth of bulges. So, I wonder if there's like a good photo I can show of just like the Milky Way's bulge. Oh, I guess this is probably a good example. Like, for this Sombrero galaxy, you can literally see that there's like a bulge like sticking out here. That is what it's referring to. But basically, there's been a big question about like, what are the roles of these clumps of these first galaxies? And I think it's interesting that they point out that this can contribute to the growth of bulges, because if I recall correctly, there has been some conversation that has been sort of denying this idea. But that being said, maybe I should check the literature to see, you know, what exactly... I think there's like a lot of theories on what the clumps directly lead to. Oh, wow. Wait, this paper has so many cool clump diagrams. Oh, I would love to show this, but I need to check the copyright. Yeah, I'm not sure, so I don't think I'll be able to show it. But if you go into the paper, they have some gorgeous photos of these clumpy galaxies. All right. Yes. Like at the center of galaxies, yes. I thought bulges were due to galaxy mergers. Yes. Though, I think that's one of the reasons why this idea of like... I mean, clumps could be also formed from galaxy mergers. So it's kind of like, is it the chicken or the egg, right? Like, which one came first? Like, are clumps a result of mergers? Or Are clumps the result of mergers, or are mergers the result? Well, mergers are definitely not the result of clumps, but well, it's more like, do the clumps create the bulges of galaxies? Or are the bulges of galaxies created by galaxy mergers, which also create clumps? So let's see. On the horizontal axis is the clump mass, and the vertical axis shows how common clumps are each mass. So we're getting, whoa, these are some really massive clumps. For context, the Milky Way is like, what, like 6 times 10 to the 11 solar masses, I think? Oh, no. No, the Milky Way is 1.5 times 10 to the 12. Then the LMC mass, I thought, was like... LMC is 2. Where did I get 6 times 10 to the 11 from? The LMC mass is... So the Large Magellanic Cloud, which is one of the satellite galaxies, that mass is around, like, here. So these are pretty massive. Some of these are more massive than, like, dwarf galaxies. So for the younger galaxies, there's definitely a steeper slope. Oh, no, for the younger clumps. And then for the older clumps, they kind of last longer and are more massive. So why do clumps matter? Yes. Studying how clumps form and die is key to understanding how galaxies build their structure. Long-lived massive clumps can move gas and stars inward and fuel bulge growth. If most clumps are short-lived, on the other hand, then their light marks only brief flashes of intense star formation. Imaging alone cannot yet tell whether these clumps are truly bound structures or merely overlapping bright regions along our line of sight. Future James Webb spectroscopy will reveal their internal motions and chemistry. So this is basically, you can get a spectra, or sort of the flux of light at every wavelength. But instead of getting it for the whole galaxy, you can do it for different regions. And so you can sort of compare the regions with clumps versus no clumps. Helping distinguish clumps that formed in place from those brought in by mergers and interactions. These results lay the groundwork for those future tests, offering a statistical view of how clumps form, evolve, and fade within their host galaxies. I think that's it. Yeah, no, this is great. Yeah, super cool stuff. Clumps are super duper interesting. Long live the clump. Yep, exactly. But I think these clumps are bound structures, just coming from like a cosmological simulation standpoint. Some of these simulations have been able to reproduce these clumps and show that they are sort of bound. Though only time will tell. I think this additional measurements will be incredibly helpful for helping us understand, like, what are the role of clumps in these first galaxies. So thank you, Nilufar Sharay, who is actually studying how galaxies grow through star-forming clumps. When I'm not thinking about cosmic blobs, I'm reading, hiking, or listening to Bach. That is so funny. Is Nilufar on this paper? I don't think so, yeah. Okay, cool. Well, thank you for this really fun read. Yippee! One article done. Nilufar, that is a Persian name, yes. I think so. Alright, let me just... Yeah, so we have one that is not related to... So our next article is also on clumps, but it is on black hole clumps. I think. I actually haven't read this yet, so I'm just gonna say black hole clumps and then we're gonna figure it out. That first Astrobite was not as sus as last time. Oh, that was such a great stream. For those of you guys who don't know, I did an Astrobite stream on exoplanets, and the protoplanetary disk was basically the precursor to how how planets form look like in Among Us. And that whole stream was so much fun. There was so many really great you know, puns and stuff. I think they were like unintentional though. Okay. Let me get some water. Amogus, yes, no, Amogus is great. Wait, let me see if I have the, yes, the Amogus. Puns, you say. I don't think they were intentional, though. Scientists do have a sense of humor. Speaking of Among Us, I have been prepared. I know I haven't done a live lecture in a while. These Astrobites streams have sort of been like a live lecture in a sense, but I haven't done a real live lecture in a while. But I've been prepping one for the Boomerang Nebula. And if you don't know what that is, it is the coldest place in the universe, and you know what? I'm just gonna show it. I'm just gonna show it. This is such a beautiful photo. Let me just get it out in a new tab. So this is the coldest place in the universe. Well, okay, actually this was a photo I believe taken in 2013 or 2010 or something like that. And the updated photo with higher resolution does not look like this, unfortunately, but my ex must be from there. That's crazy. Must have vented. Actually, oh, I don't want to give too much of a spoiler for this, but the reason why the Boomerang Nebula is so interesting is that it actually has two jets that are venting out material from it and are sort of plowing holes in the surrounding gas, which is why it kind of looks like this hourglass shape if you see the purple background. Oh, it's so bad. But I love it. I love it. It's so gorgeous. So I've been preparing a pretty chill live lecture for that. Honestly, the sad thing about this nebula is that there hasn't been as much... there's a lot of active research on it now, but yeah, it's really interesting to understand like how stars die, because this is actually formed from a remnant of a dying star. It's venting. No, literally, it literally is venting. No, it is so sus. Because it's also the coldest. So you think, right? Like if it was, you know, blasting out these giant jets into space, that it would be like this really energetic system. But it's actually the coldest place in the universe. And that has to do with a little bit of physics. So if you want to learn more, be sure to pull up to the live lecture. I think I'm going to try to aim for early March, end of February. We shall see. So yeah. How does this keep happening? What do you mean? Like the Among Us content? The hype is so real. I know. I'm so hyped. I actually had to do quite a bit of background research to prepare for this because I actually knew nothing about this nebula. I think you Orbeez were the one who also told me about this nebula. This was, I think, a few months after I debuted. The Space Among Us, exactly. Is it because the jets are making things super diffuse? No. Okay, I'll give like a one-sentence summary. It's because the jets are ejecting so much material out of the star. And... oh, okay, I can't do this in one sentence. It's because of this process known as adiabatic cooling. When gas is ejected at a very high rate from an area of like high to low pressure and no extra energy is added to the system, it needs to move apart, but it doesn't have the energy to do so. So it extracts that energy from its own molecules, which is how it's able to cool to temperatures below the 3 degrees Kelvin, which is like the temperature that's like that permeates the universe. So it's colder than the vacuum space itself. Thermo stuff. Yeah. I go into this a bit more detail in the presentation. You Orbeez are making me spoil everything. Grr. I'm angry. It's okay. It's okay. So stay tuned for that. It's gonna be great. All right, I think we should go on to our next article. I think this one, yes, so this is not about, oh no, it is about clumpy galaxies. I actually haven't read this one yet, so we will see how this goes. Sorry, no, it's okay. How cold is it? Is it like negative? No, it is around 1 degree Kelvin. You can't go less than 0 degrees Kelvin, because 0 degrees Kelvin is absolute zero. That is the point at which all atomic motion ceases. Yeah, no, it's super cool. I absolutely love it. And I wouldn't have known it without you guys, so thank you, Orbeez. Alright, so our next article for today is Smooth Like Cosmic Butter. Oh, I think this is a BTS reference. How AGN destroyed molecular gas clumps in galactic nuclei. Written by Margaret Verico. Cool. Okay. Background. Okay, so let's get a reading. We specifically point Z to Among Us things. What can I say? I do love Among Us, that is true. 0K doesn't exist because of the high... I think exact 0K doesn't exist, but I think we can get very darn close to it. I'm gonna quickly look this up because somebody did ask me about this today and I didn't have an answer. What is the closest we've gotten to 0 degrees Kelvin, like scientifically? New record for coldest temperature. What's the coldest for lowest temperature achieved? I'm not really sure what the search query is for this. Lowest artificial... What? That is crazy. The lowest temperature that matter has been cooled to is 38 picokelvin. Just 38 trillionth of a degree above absolute zero. Wait, I'm gonna pull this up. I'm gonna pull this up on this side. This is on the Guinness Book World of Records, so you know it's a reliable source. The temperature was achieved by a group of researchers from Quanta's team. Oh, I realized that. Oh no, the thing is a little cut off, but here, let's see. The results were published in 2021. They achieved this low temperature by cooling rubidium atoms into a state called a Bose-Einstein condensate. They did this using a technology called a time domain matter wave lens system, which uses magnetic lenses to hold the atoms still and thus reduce their total energy. What the heck? That is so cool. Wait, it was launched? The whole system, this thing that was 38 picokelvin was encased in a shockproof cylinder and then just casually launched up this drop tower. The last aspect enabled them to replicate the conditions of space and sap a tiny bit more energy from the atoms. That is crazy. Still warmer than my Valentine's? No. That's so sad. Have it and give it to the next one. Yes. Time domain matter wave lens. That is such a sick name. Imagine just being like, yeah, no, I'm working on the time domain matter wave lens system. Or I gotta lock in on the time domain matter wave lens system tonight. Like, that's so sick. Like, what in the sci-fi? That's so cool. See, this is why physics is so cool. You also get these really cool names. Like, I've also talked about, like, the extremely large telescope and stuff. Like, people get really creative with names. Oh, shoot. This is great. Let me go back to the original article. Yeah, this is sick. I mean, I think one of my favorite words in physics is, like, people who do plasma physics do, like, tokamaks or stellar raiders. Like, that's just such a cool name. Laser Interferometer Gravitational Wave Observatory. LIGO is a pretty cool name, yeah. Technobabble. Just call it the cooler. The name sounds like... Well, I feel like there's a lot of backronyms in astrophysics. Like, basically acronyms to sound like certain things. Like, for instance, oh, I mean, even in planetary science, like the radar on Europa Clipper is reason. And then there's like another instrument called rhyme. So there's like rhyme and reason. But it's not spelled like... Oh my god. I looked up rhyme and reason and I did not get anything related to Europa. Passive sounding modes. Yeah, I guess I can't find it right now, but yeah, there's like a radar system. It's called rhyme and reason. Waiting for the Z machine to be rebuilt. Oh my god, that article on the Z machine was great. Yeah, there's a gene called Sonic Hedgehog. And yeah, no, that is true. Science just thinks of cool names. I think just scientists are very creative when it comes to naming things. What can I say? All right, let's read the next one, or we're gonna be out of time. So let's go. Galaxy quenching, or the process by which galaxies shut down star formation, is still a bit of a mystery. While we know that galaxy mergers, massive dark matter halos, and supernovae can shut down star formation, simulations still require a process called AGN feedback, or like black hole feedback, to prevent massive galaxies from starting up their star formation again. This feedback occurs at the supermassive black holes at the centers of galaxies, accrete gas, forming this bright hot disk and launching winds or jets into the gas at the center of the galaxy. These active galactic nuclei can therefore disrupt the clumps of cold gas in massive galaxies, and since these clumps would otherwise collapse to form stars, AGN feedback is thought to play an important role in shutting down star formation. So it is very important for us to simulate these supermassive black holes at the center, because they are an important key to understanding how galaxies regulate their formation of stars. Hello, Snaggle Fluster. Thank you so much for joining chat. I have a question. Yeah, feel free to let me know. But there's a catch. Observational tests of AGN feedback paint nearly the opposite picture. These black holes tend to live in galaxies with lots of ongoing star formation, since the same gas that fuels the black hole also fuels star formation. Black holes also, the AGN also only live for a short time relative to star formation, about 100,000 years, compared to the tens of millions of years it takes for galaxies to form new stars. So it's likely that that it takes several episodes of black hole activity for AGN feedback to take effect. So how do we observationally test these theories of AGN feedback? See, look, this was definitely a backronym. Galaxy Activity Torus and Outflow Surveys, or GATOs. Like, that was definitely a backronym. That's such a cool name. The GATOs team uses radio imaging to observe molecular gas in the vicinity of AGN in nearby galaxies. So they actually observe these supermassive black holes. They look for these signatures of AGN feedback on very small scales. Tens of hundreds of parsecs, where one parsec is about 3.25 light years. These scales reflect the environment in which the AGN impacts and is impacted by gas during one episode of activity. In today's work, the GATOs team uses molecular gas clumps, where star formation is likely to occur, to test whether these supermassive black holes can disrupt star formation in the nuclei of nearby galaxies. El meow, yes, exactly. So clumpiness is already on. Please tell me the GATOs team mascot is a cat. Wait, hold up. Yes, it is a cat. Wait, I'm just gonna pull up the image. It's so cute. It's like smiling. It's like smirking too. This is great. Wait, I think the best group name that I've heard, wait, I gotta give solid credit to this. Oh, shoot. Oh my god, this is gonna take me down a rabbit hole. Genius, I love it. Yeah, no, it's great. Hold up. Oh my god, wait, I'm like trying to find this and I am struggling. Yes, okay. Let's go. This is my favorite. The Boba Lab at Amherst College. I love it. It's so creative. It's so cute. And like, look at that little logo. Like, doesn't that just look so inviting? Wait, I actually wonder what it stands for. Oh, I thought it stood for something. Shoot. No, just no what? Oh no, there we go. The baby objects with baryons at Amherst. So they're basically looking at these like very low mass dwarf galaxies. So baby galaxies, object with baryons. Also, many of the lab members like, well, do you like it? That's so cute. That's just so whimsical. I love it. I want to work there even though I don't have a STEM degree. That's the best. I know, it's so cute. I wonder if they get like boba for their group meetings. This is great. Anyways, that was such a tangent. It's so cute! I know! Well, the Gatos team also deserves a lot of credit. Prerequisite to join is to like boba, yes. Oh, thank you, Snaggle Fluster, for the question. Oh my god! Whoa! Hello, Actual Education. Thank you so much for the raid. Thank you so much for reading. Oh my god, I really appreciate it. Alright, well, I'll do a quick introduction. Speeding at Seeds, me Z, hello. I am an astrophysics VTuber. Basically, I do IRL astrophysics research, focus on galaxies, and I also do content on physics, engineering, space policy, etc. Thank you, Raiders, for joining on Twitch. I really appreciate any support. I actually primarily stream. I don't know if I should be saying, you know, what my primary platform is, but I did start out on YouTube. So if you want to check me out there, I have long form. Oh my god! Thank you so much. We reached our follower goal. Thank you so much. I have long form videos on my YouTube channel, so please go check those out on science policy, galaxy evolutions, relativity, and so forth. I stream on all three. On all three? Three? There's another one? Well, thank you so much. I really appreciate it. Let me give you a quick shout out. Oh, TikTok, I see. Science. Well, what were you streaming beforehand? I guess given your name, you also do educational content as well. We are currently reading an article about clumpy galaxies. Oh, I'm already following you. Great. Perfect. We were just helping on all sorts of STEM tutoring. Oh my god, that's amazing. See, I wish I had something like that, you know, when I was first starting out in science too. Calc, physics, etc. Well, that's amazing. I did get a question in chat from Snagglefluster, and I was gonna say that unfortunately, this quantum physics question is a little bit out of my area of expertise, though maybe actual education and tutoring might be equally helpful. But yeah, we were learning about clumpy galaxies. We're going to be taking a look at this article. But yeah, so this is a website known as Astrobites. It is a website that takes existing research papers in astrophysics and sort of translates them in a way that is more accessible for the general public, or if you're first starting out in astrophysics. And I find it to be a very, very helpful resource if you want to get into reading papers every day, especially because it can be really technical at the start. And this paper, these articles also link to like definitions where you can learn more about a lot of these different terms. So we just got to the point where we were describing AGN feedback, or specifically supermassive black hole feedback. And that is useful because it can disrupt these big clumps that we're seeing in the earliest galaxies in the universe. clumpy via n-body simulation or something else? Well, actually, clumpiness has, in our articles that we've been looking at today, clumpy galaxies have been actually observed in the early universe by telescopes like the James Webb Space Telescope. Though I do have to say that we have also been noticing clumpy galaxies emerging in our simulations as we have been gaining more computational power, which seem to match the observations of the early universe. The real question is why these clumps emerge and sort of what role do they play in assembling the first galaxies. And in these simulations, there aren't just n-body simulations, but they are like hydrodynamical simulations, in which sort of like gas flows around. So it's a lot more complex than just an n-body simulation per se. Good afternoon, Ambience. Thank you so much for joining. All right, so now that all the raiders are on board, I think we should keep on reading. So we just got up to the point where we were introduced to the Gatos team, which uses radio imaging to observe the molecular gas around the black holes of nearby galaxies, inside the galaxies. And they are using these radio observations to understand how supermassive black holes disrupt star formation. All right. So clumpiness is already an important measure in astronomy. The techniques used in this paper were originally developed for measuring galaxy clumpiness, not gas clumpiness. Since stars form in groups in molecular gas clouds, star-forming galaxies tend to have bright clumps. As time goes on, the groups of stars drift apart, smoothing out the clumps and leading to a smoother light profile in non-star-forming galaxies. Similarly, clumps of molecular gas indicate regions where stars are likely to form in the future. Yeah, we just read about that in the previous article. While smoother molecular gas distributions indicate gas which is not collapsing under gravity to form stars. So how do we measure whether a material, or in our case like a galaxy, is clumpy or smooth? So they determine the clumpiness parameter. So this is a pretty well-defined parameter. So basically you kind of fit a Gaussian over the galaxy, a smooth image using a kernel, and then you subtract the smooth image from the original, and then you divide, I think you divide by the original again. And so as you can see here, we have the original image here on the very left. And then after we smooth it, the clumps kind of pop out. And then when we subtract it, you can see that the clumps are literally like sticking out here. And this makes the clumps smaller and it lets the clumps pop out. So in figure 1, you can see how the Gatos team measured clumpiness in their sample using this very common technique from galaxy studies. I've been playing with CFDs as part of my interest in ocean wave power just as an amateur. Well, that's super interesting. I think it's one of the really cool things about galaxy formation simulations is that and maybe even any hydrodynamical simulation in general, is that the base of it is CFD, or computational fluid dynamics. And so there is a lot of overlap in, like, one of the coolest things I saw was there was some overlap between, like, simulating how F1 cars, like Formula 1 cars, like how the air travels above the car, and simulating the first galaxies in the universe. Like, it is basically the same physics, like very vastly different scales, vastly different equations. There's, you're not thinking about like the cosmological expansion when you're simulating a car, but at its base, like, the equations of hydrodynamics are consistent. And so sometimes, I get asked, like, how do we know if these simulations are reliable? Like, what kind of assumptions are you making? Well, the same equations that we are using for fluid dynamics are also the same ones that help us predict the weather. And so there's a lot of overlap, which is super fun. I'd wonder if n-body works on massive scales. It feels like you'd have to account for relativistic effects at that size. I mean, a lot of these simulations do have to account for relativistic effects, especially if you're dealing with extreme systems. Like, I do know somebody who's been working on, like, black hole simulations, and those are very extreme environments. CFDs are amazing, so fun to run. Yeah, no. And I actually thought about doing a stream where we just, like, create a very basic cosmological simulation, though like, there was definitely a lot of concern with like copyright and like whether this data is like publicly available and so forth. But it would be super cool to do that. All right, so let's keep on reading. So they started by adjusting all of their images to the same spatial resolution, 16 parsecs. They then create a set of smooth image using kernels of different sizes. So like Gaussian. And basically they did what they did in the figure above. They then subtracted those smooth images from the originals. When they do this, the clumps that are smaller than the kernel size stand out in the image while the smooth background disappears. By using kernels of different sizes, they're able to study the way that these supermassive black holes, or AGNs, impact clumps on different scales. So they actually, wow, they use 3 different ways of calculating the clumpiness. Method 1 is sensitive to the fraction of the nucleus that's filled with clumps, while methods 2 and 3 are more sensitive to the amount of gas in the clumps versus in the background diffuse gas. So I guess they were very meticulous with how they defined clumpiness here. They use these 3 metrics for the whole nucleus as well as for the 2 apertures shown in figure 1. These apertures are at 50 and 200 parsecs, representing the immediate environment of the AGN and the broader gas structures fueling the AGN respectively. Now that they have measurements of clumpiness on different scales, and within 2 different apertures, the authors can study how the AGN impacts the molecular gas in the nucleus. Okay, great. So they're using these different measurements in order to extract information from differently sized clumps. Flow is amazing, yes. I've been meaning to study nonlinear PD series, but I have to get to the linear parts first. That is so valid. And I love your username, by the way, Convergent Series. That's so cool. First, the authors measured the clumpiness within 50 parsecs and find that more luminous AGN have smoother gas in their immediate environments. They find that the clumpiness on small scales is Oh, thank you, Truly, for following. They find that clumpiness on small scales is anti-correlated with luminosity. Clumpiness on larger scales has a mostly flat relationship with luminosity when AGN aren't very bright. But once they cross a luminosity threshold, about 1 billion times the energy of the sun, their clumpiness decreases dramatically. That's interesting. So once the supermassive black holes reach a certain level of energy or luminosity, their clumpiness decreases. This is a similar threshold to that found in an earlier paper by the Gatto's collaboration, where gas becomes less centrally concentrated once the AGN is brighter than this limit here. Interesting. This may indicate that there's a threshold at which the AGN begins to blow away and destroy gas in its immediate vicinity, carving a cavity in the nucleus. This gas that remains heated by the AGN, which makes it less likely to form stars. So in order to form stars, you need a lot of cold gas, and you need it to come together and become very dense, because then fusion is able to start and stars are able to be born. But when you have a cloud of gas that is very heated, that material can never coalesce together. In addition, if you have a cloud of material that is like very diffuse, you also don't have enough material to start fusion as well. And so what this is indicating is that the supermassive black hole at the galaxy's center can affect the gas in its immediate vicinity, which, if you think about it, is such a cool concept, right? This tiny little black hole at the center of the galaxy is so energetic that it's able to affect the formation of stars in this whole surrounding region. Cast Iron asks, is this gas being ionized then? I think so. It just says heated. I'm not sure if it ever reaches the point of being ionized. I do know that like the gas around the disk of the black hole itself is ionized, but let me see how far that expands out. Out to several kiloparsecs. Getting very differing results online. I think it might be up to several kiloparsecs that it ionizes the gas. So yes. So the gas is ionized, and of course, that is detrimental to sort of having the gas coalesce to form stars. The relationship between AGN luminosity and gas clumpiness. Colors represent the size of the kernel used to create the background image. So yellow lines show the clumpiness on small scales, while the purple lines show clumpiness on large scales. So, okay, so clumpiness decreases with the luminosity of the black hole. So the luminosity of the black hole is on the x-axis here. And so it is really dramatic for this, yeah. With the most dramatic effects occurring for larger molecular gas clumps around very luminous AGN. Cool. Next, the authors measure clumpiness in the 200 parsec aperture. They still find a negative correlation between clumpiness and AGN luminosity, but without the same luminosity threshold. When they measure the clumpiness of the gas between 50 and 200 parsecs, they find almost no correlation. Okay, interesting. So before we were saying that there is a really strong correlation between the clumpiness of the galaxy in the surrounding region and the supermassive black hole's luminosity. But now, when they look at 50 to 200 parsecs, there is no correlation. Wow, no, that's pretty shocking. So that means that clumpiness still decreases, but not as much as within the 50 parsec. So that kind of makes sense. So within the 50 parsec region, it's like very strongly affected. So the authors of today's paper believe this indicates that the AGN is directly impacting the gas within 50 parsecs, while the more distant gas reflects the properties of the infalling gas from the host galaxy. So I guess to go back to Cast Iron's question, the region at which the black hole affects the surrounding gas is definitely limited. But 50 parsecs is an incredibly long distance. And it's kind of crazy to think that the supermassive black hole at the center of a galaxy is so powerful to affect gas in that surrounding region. So let's read on. The authors posit that gas in the inner 50 parsecs is a mix of inflowing gas from the galaxy and gas that has been heated and blown away from the AGN. At low AGN luminosities, the AGN can somehow impact the gas, dissolving some of the smallest clumps while the larger clumps survive. So the black hole literally dissolves the clumps. Is there a quantitative measurement for clumpiness? Yes. That was described earlier up here. They determine a clumpiness parameter. There's a well-known clumpiness parameter from this paper. Basically what you do is you kind of fit a Gaussian over the galaxy and you subtract the smooth image from the original, and that lets the clumps pop out. And you can sort of determine the brightness of these clumps, and I think you like sum them together, or you, yeah. It's just like an image processing technique to extract the clumpiness as a number. So that's why they're doing the clumpiness metric here. All right, let's see. At higher luminosities, the black hole overpowers the gas inflowing from the galaxy. Oh, wait. Oops. Where were we? Oh, yes, we were here. Destroying even the larger clumps where stars are most likely to form. So if we have a supermassive black hole that is an even higher luminosity, it destroys the even larger clumps. But this is all within the central, like 50 parsec region. The gas that is more further away, so 50 to 200 parsecs away, is less affected and reflects whatever state it was when it started falling from the larger galaxy towards the black hole. Conclusions. The results of this paper, as well as the results of the previous work by the Gatto's collaboration, show that AGN can have a powerful impact on the gas in galactic nuclei. By smoothing, heating, and expelling gas from galaxy centers, AGN might be suppressing star formation at small scales. However, the impact of several episodes of black hole accretion on larger spatial scales in massive galaxies are still an observational challenge. Luckily for those of us that study galaxy evolution, there's still lots of work to be done, testing models of AGN feedback with observational astronomy. Amazing! So that was our article. Thank you, Margaret Verico, who actually studies supermassive black hole transients. That's super cool. Hello, A. Idolus. Not a fan of one parameter measures, especially when they're talking about large and small clumps. Well, they actually examined three different, so they used that metric, but they actually used 3 different ways of measuring the clumpiness that are kind of sensitive to different things. They have one method that is sensitive to the fraction of the nucleus that's filled with clumps, and then they have one that's sort of comparing the amount of gas versus the background. That being said, Dojo, you do bring up a fair point, especially because there are certainly clumps that are a very small size. And I think in the previous Astrobite that we read, one concern of these measuring clumpiness is that for galaxies that are further, I know that they didn't really look across time for this paper, but if we're looking at clumpiness across time, it is much harder to see clumps from galaxies in the early universe because they are more further away and they also tend to be smaller. And so we're getting smaller clumps from them, right? So that's also another factor to be conscious about. Where do you read articles, Sci-Hub? Well, if you go into the pinned comments, this is an Astrobites article, but do you mean just in general? I'd say like, for those of you who are interested in like starting to read papers regularly, I would recommend Astrobites, and there's also other bites that they do. I found out the other day that they have one for like ocean like studies, which is pretty cool. But if you mean just like in general, where do I read like research papers? What I do is every morning you can sort the archive by your category. So I just go through my category and just like sort by recent. So that's great. Another really great way to search for articles is also known as ADS. I think they renamed it. They're revamping to SciX now. That is basically the main way that astrophysicists search for articles. Thank you, Margaret. Yes. Well, I hope, Eggy, your essay is also going well. Or went well. I think 30 minutes passed. I think... Yeah, that was basically all the articles I had for today. I did have one more, but this one actually was not related to clumps. So I felt kind of weird about adding this one. So I think we might just end on this. It's submitted. I'm now playing Uma Musume as a reward. Well, congratulations. Yes. I'm glad I was able to stream today in the evening. I know my past few streams have been collabs, and it's a little harder for me to chat while collabing, but they've been so much fun. So my last stream was with Kim, and we were writing a little paper on Europa, and we've just been like messaging back and forth to try to have the PDF uploaded somewhere nice, which might be cool. So yeah, woo plug. Yeah, no, I mentioned this at the start, but wanted to mention it again. If you are a VTuber or streamer passionate about science communication and you want to join this amazing group that I'm part of very like-minded creators, if you go to my X account, actually, let me just pin it for now. Yes. Oh, wow, it got a ton of reposts. Let me just pin it now. Yeah, I'm gonna spend a few minutes chatting real quick. But if you go to that link, you can see the link to our interest form. That is not an audition form. That is not, you know, an evaluation form or anything like that. It is just sort of a way to indicate that you're interested and make sure that it's also useful for us to make sure that you'll be in the loop for any other notifications moving forward, especially as we start with the audition process. And you will be part of a new generation. So Mylan and I are part of Gen 1.5. We are still brainstorming for a new generation name. But if you're interested, please do fill out the form. We have already gotten so many responses, which is absolutely amazing. I've probably mentioned this like a quadrillion times now, but you know, when I first started VTubing, I didn't realize that there were, you know, this many people like interested in like scientific communication using VTubing as a platform for that. And I think VTheorem has been an amazing home for it. So I really highly recommend that you sign up for the interest form, and it is not binding. So even more reasons to fill that out. So yeah. So in terms of schedule, I mentioned this at the start of stream. I don't know if I'm going to be streaming this weekend. I guess maybe I'll hint at this because you Orbeez have made it to the end, but I got some last minute Valentine's plans. So, that's kind of the reason why things have been like up in the air. So we'll see, you know, if I decide to stream something on the weekend. But the next stream that will be coming up soon for sure is celebrating 7K with the Kerbal Space Program stream. Ooh, yeah, no, that is the only appropriate response to that. Thank you, Eggy, for your enthusiasm. ZB slaying. Z's got Riz. I know, well, okay, I always joke about not having Riz, but I promise you guys, I do have Riz. Congrats on Valentine's. Well, no, nothing to be congratulated by, I guess. Yeah, no. I'll keep you updated. It's gonna be great. It's gonna be great. So yeah, I mean, I know I don't usually talk about this kind of stuff on stream, but if you are curious and want to hear more, I will be more open to talking about that. But yeah, so that's basically the reason why the schedule this weekend is up in the air. I know I was originally planning to hop on Nep's stream, but I also realized that Nep is streaming right now. So we might as well just like raid for fun. That could be cool. So let me set that up. So if I do not see you all in this weekend, I hope you all have a great long weekend for the American Orbeez because of President's Day. And for everybody, a great Valentine's weekend. Let me see. Okay, great. So if you are not on Twitch, please hop on so that we can support Nep, because I think she is doing a 2K push. So, oh, I guess I didn't. Oop. I don't know why my Twitch command isn't working. I just manually pasted it. Yaycation, yeah, exactly. So please hop on the Twitch side, and I also dropped the raid message. Let me drop that again. And yeah, I will see you guys in the next one, and maybe I'll have some fun updates about my Valentine's plans. So until next time, I will see you guys later. All right, bye-bye. Oh my god. Oh, wait, let me quickly check them what it is. Oh, thank you, Cast Iron, for following. Okay, bye-bye for real. Bye-bye. See you later. Bye.
Though I'm trying not to wander, gazing up into the sky, though my heart has not recovered, take it one step at a time. With the memories I'm left with, I don't know how to describe. Seasons change, but I'm still left here. Take it one step at a time. I know that things I say have changed, more with each passing